Hello, my name is Pierce Dara, and on behalf of William Hatch and Eric Eide, I'm very excited to present to you about our paper on Clotho, a new Racket library that enables developers to use parametric randomness with ease. So I guess the first thing we should address is, what is parametric randomness, and why should you care about it? Let's find out. In the paper, we define parametric randomness as a kind of random value generation that is amenable to predictable external manipulation. Practically, what we mean by this is any system of random generation wherein the user can deliberately influence the outcomes of otherwise random generation events to bring about discrete structural changes in the resulting output. In some sense, this is like being in control of the destiny of your program even when randomness is concerned, hence the name. Clotho was a Greek goddess responsible for spinning the thread of humans' lives that determined their fate. I think that definition of parametric randomness is not very helpful, though. I prefer learning by example myself. Here, we have a small Minesweeper game. If you don't know Minesweeper, that's okay. All you need to know is that it's a single-player game where the player attempts to identify the locations of a number of mines hidden across the board. For this implementation, the player is controlled at random, simply choosing any of the 9 squares until either the game is won, all squares without mines have been chosen, or an invalid move is made, such as choosing a square where a mine is hidden, or choosing a square that was chosen before. There are 3 mines hidden somewhere in these 9 squares. The player's objective is to select the other 6 squares without disturbing the mines. The first move the player randomly makes is A2, the top middle square. There isn't a mine, so it's considered successful. Nice! Let's make another selection. The player randomly selects B3, and it's also a successful move. And now B1, which is another success. We're really on a roll. Uh-oh. Looks like the player randomly selected B2, which was hiding a mine. Darn! And it was going so well, too. Well, it's about time we learn about this parametric randomness business. Let's replay the game, but while looking at the game's decision tree at the same time. Here, we're looking at 2 things. On the left is the current state of the game, and then on the right we see all of the available options that the player could make right now. The 3 squares where mines are hidden are shown with red backgrounds and a bomb. We hope the player doesn't pick any of these. The valid options that will progress the game towards a win state are shown with blue backgrounds and a gray check. We're just replaying the earlier game, so we'll move forward to when the player has selected the first square, A2. The player made the choice, which we see reflected in the current game state on the left. On the right, the options that the player didn't pick last time are shown slightly translucent in the top row of boxes, and the bottom row shows the available moves the player could make next. Note that A2 is an option for the player since we are assuming a naive implementation of the game, but taking this path would bring about an end to the game because it's an illegal move. However, we know the player randomly selects B3. I've eliminated the extra boxes from the first selection to reduce the visual clutter for the moment. But remember that we're only looking at one branch point at each level of the game. In actuality, all of the blue checkboxes have their own subtrees with many more potential paths through the game's possible states. It's quite complex. Anyway, we move forward to the player's selection of B1. Nothing surprising here, I think. But finally we come to the end of the game, when the player selected the square B2. A square with a mine hidden in it. Remember, there were a lot of other paths through this tree of possibilities. This could have played out very differently. If we wanted to, we could rerun the game from the beginning and hope that new random options would be chosen to select a different path through the tree. This is a common strategy when exploring a very large state space. You just make random choices and hope to stumble upon a branch that is interesting, which, in this case, would be a branch that ends in a win. We think this is a bad solution for some kinds of problems. For example, if we want our Minesweeper player to win, why should we throw away 3 perfectly good moves? Why start the exploration over at the root of the decision tree? This is inefficient. Clotho instead allows you to rerun the sequence of random generations, but mutate only specific outcomes so that you can explore more paths similar to one you've already explored. We are effectively reducing the size of the problem space by constraining our decision tree to a subtree with a predetermined prefix path that is known to be good. This reduces the number of possible explorations by a significant amount. To enable this style of random generation, Clotho associates each random generation event with a parameter, shown here in boxes labeled P with subscripts. These parameters are combined into some kind of internal representation, which can be used as an input to the game function or a driver function when that's easier. In this case, the particular combination of parameters resulted in the player selecting a square with a mine in it and losing the game. By modifying a specific parameter, the course of the program can be altered at a specific point. Here, we modify the parameter corresponding to the random selection that caused the player to lose the game. Now, the player selects a different square as the fourth move, but we didn't have to re-explore the whole decision tree to make the first 3 moves. Instead, we preserved those moves and simply made a new selection for the 4th move. Maybe this modification to the parameter will even cause the player to win the game. Now we can summarize what parametric randomness really is. In a parametrically random system, you can start by generating an initial sequence of random values, which are automatically correlated to parameters that are exposed to you. If you happen to like part of the result of that sequence of generations, but not all of it, you can tune specific parameters and rerun the program to observe the outcome. Doing this allows you to quickly explore decision trees for random problems where interesting paths are clustered together. We think this parametric random generation could be very useful in some problem domains, like our own, which I'll come to in time. So now that you know what parametric randomness is, let's talk about Racket's built-in support for random generation and see how we can make parametric randomness work. Practically all randomness in the Racket standard library is controlled through a single arbiter of random state, the current pseudorandom generator parameter. Influencing Racket's randomness anywhere requires manipulating this parameter. Note that this use of the word parameter refers specifically to the Racket concept of a value that can be modified thread locally without affecting external scope. There's a link at the bottom of this slide to read more about it if you're not familiar with the concept, but all you really need to know is that parameters are one way of providing singleton objects used for managing the state of something. Racket provides 2 ways to construct a new pseudorandom generator that can be used as the current pseudorandom generator. One creates a new random state with no user input at all, which is clearly not going to help us because we can't manipulate the construction. The other takes in a vector and uses that to initialize the state of the generator. Unfortunately, the rules for that vector shape are very specific, which means that we're really only setting the initial state and then letting the random generation follow whatever mathematical model it uses internally. We have no control over specific generation events. There is also the random seed function, which lets us manually set the seed from which random values are mathematically derived. Like the vector we just talked about, this function doesn't really give us fine-grained control over each discrete generation event, and that's crucial to achieving a simple parametric randomness system. These are essentially all the ways Racket provides to manipulate the random generation of values. So what can we do with this? Well, when we were initially trying to solve this problem, we saw 2 potential solutions. The first idea was to simply extend the pseudorandom generator in some way to support our desired functionality. If we could just build a new variant of the pseudorandom generator and install it into the current pseudorandom generator parameter, we should be able to use all the other existing randomness functionality in the standard library, as well as anything else, in addition to whatever extra functionality we wanted to provide ourselves. The other option was to build an entirely new randomness system from the ground up. Building a new system seemed like way more work for not much benefit, so we decided to extend the pseudorandom generator. Keep things simple. Unfortunately, we discovered that the pseudorandom generator is internally built as a struct that does not expose its fields or methods beyond its declaring module, and the current pseudorandom generator parameter will not accept a value that isn't an instance of this struct. But building an entirely new randomness system wasn't the right approach either. We wanted to be able to use parametric randomness with other libraries that relied on Racket's built-in randomness functionalities. If we built a new custom system, we would have to essentially re-implement those libraries to use it. Neither system was going to work for us, so we settled on a hybrid approach. Build a new system that uses the current pseudorandom generator behind the scenes in such a way that existing libraries could benefit from it. Which brings us to the part of the talk where I tell you what we developed and how it works. The core functionality of Clotho's parametric randomness is handled by a struct. The struct, which we call the random source struct, consists of 4 fields. First, and perhaps most importantly, is the BTS byte string, which contains an encoding of the randomness parameters we talked about in the Minesweeper example. This byte string is guaranteed to always have at least 4 bytes, which we'll come to in a moment. All of the critical functionality of Clotho derives from this field. Next is an integer index into that byte string. This is used during playback-style random generation, where we simply use the values encoded in the byte string. Third is the PRG, a Racket standard pseudorandom generator. This pseudorandom generator is seeded with the first 4 bytes of the byte string that we mentioned previously. If there are enough random generation events to exhaust the byte string, which is, after all, finite in length, further values will be generated using this pseudorandom generator. It's crucial that this generator's seed is recorded in the byte string because this ensures that reruns with a limited byte string are deterministically consistent with one another. And lastly, we have the add list. When the byte string is exhausted and new values are generated from the PRG, we cons those new values onto the add list for safekeeping. When the user eventually requests the byte string, a functionality we'll discuss in more detail shortly, the contents of the add list are reversed and converted into bytes to be stored in the byte string. I promised some more details about that byte string though, so let's go ahead and take a look. Earlier in this talk, in the section explaining about parametric randomness, I showed this slide. What, you didn't think I'd make a Racket presentation without some meta slides, did you? In this slide, we see how the perceived random values really correspond to parameters, which are encoded in something. And that something is what can be fed back into the system to manipulate randomness in subsequent program iterations. Well, you guessed it, that something is the byte string. Let's take a closer look at it, knowing what we know now about Clotho's internal struct. So here we're visualizing just the parameters and the byte string. Note that from this point on, we won't be looking at any specific random values generated by this byte string. Here's a concrete example of a byte string that could correspond to 4 randomly generated values. This is kind of gross to look at though, so let me convert it into a numerical representation. It's a bit better. Each integer in this visualization represents a byte, but this is just a long string of bytes now. How do they work? Clotho uses 4 byte chunks to represent integers internally, so let's divide this up into those chunks. Excellent. Now we have 5 chunks of 4 bytes each. Remember that the first chunk is reserved for seeding the pseudo-random generator stored in Clotho's internal struct, so to encode 4 random generation parameters requires 5 of these 4 byte chunks. As you might have guessed by now, each of the 4 byte chunks following the initial pseudo-random generator seed chunk is a parameter. I'll explain how the user can access and manipulate these a bit later. So we've gone over the implementation of the random source struct, the most critical component of the Clotho library, and I've shown you the details of how its internal byte string works. Let's talk a bit about how users can actually use the Clotho library. The random source struct itself is not provided externally. Instead, the struct's functionality is exposed through a Racket parameter named currentRandomSource. To ensure invariants of the struct's construction are maintained, and to avoid the complexities of multiple case-specific constructor functions, we provide a single smart constructor that can create new random source structs to be used in parameterization. The final struct supporting functionality is the getCurrentRandomSource byte string function, which exposes the internal byte string to the user. The byte string can then be manipulated as needed and fed back in to the makeRandomSource constructor for subsequent random generations. Of course, Clotho also provides functionality that actually uses the random source. The core randomness function is the aptly named random function. Externally, this works just like Racket's built-in random function, but internally, this is where the random source struct's byte string gets used to deterministically influence random generation. The details of this process are given in the paper. In addition to random, Clotho offers some convenience functions for easier random generation of common simple data types. All of these functions are implemented in terms of the random function. We also implemented some macros to support certain advanced functionality. If you need to use a function that depends on Racket's built-in randomness capabilities, maybe from a library written by somebody else, you can wrap calls to that function so that it will still participate in Clotho's parametric randomness by using the wrap external randomness form. If you want to import a library that provides a lot of these functions, such as the math distributions library that ships with Racket by default, you can use the require Clotho wrapped form when you require it, and all the library's exported functions will be wrapped with wrap external randomness automatically. Lastly, we provide a mechanism for what we call randomness abstraction. That's our own term, so I'll explain it in more detail. Let's go back to the original Minesweeper example where the player loses on the 4th move. But imagine we had played 2 more games immediately afterwards. So the player lost the first game due to picking a bomb. Then they lost the second game because they made an illegal move. And the third game they won. Because all of these games were played consecutively with a single random source, the parameters are all part of the same byte string. Let's say we decide to focus on that 4th parameter, the one that caused the player to lose the first game. So we modify it, leaving the rest of the byte string intact. Then we play the games again. It looks like the player won the first game, which is great. But the second game is lost again due to a different illegal move, and the third game is lost due to picking a bomb. This is disappointing because we had originally won that third game. This happened because when we adjusted the 4th parameter, it caused the first game to not lose at the 4th move. Since the rest of the parameters are deterministic, the entire sequence of moves shifted forward by 2. In other words, tuning a parameter earlier in the byte sequence can have undesirable consequences for later generations if that modification causes a structural change. So let's try a different strategy. We'll use randomness abstraction. What that means is that each game's randomness parameters are correlated to a single higher level parameter. We then just use those higher level parameters to build the byte string. In this example, we'd like to correct both the first and second games, but leave the third game untouched. So, we modify the appropriate clusters of bytes. When we play the first and second games with the new parameters, entirely new squares are chosen. And look, the player won the first game. More critically, though, is the fact that the third game was left completely untouched. We managed to increase the overall win percentage without having to regenerate every game. Randomness abstraction is a tool for clumping together multiple calls to randomness functions that are all used for a single purpose, and correlating them to a single parameter. For example, you can abstract the act of playing a game, as we did in the example. This could be useful if you want to use a fuzz tester for your byte string manipulations, and that fuzz tester requires its input in the form of a simple byte string. We have only just begun experimenting with randomness abstraction, so let us know if you find a good use for it in your own project. We return now to the final component of the Clotho library, hashlangs. After all, what Racket library would be complete without a hashlang or two? Actually, Clotho provides 3. For when you don't want to use any randomness, there's Clotho Racket Base. This is identical to Racket Base, except it leaves out all the randomness functionality entirely. Then there's the Clotho hashlang. This provides all the bindings in Clotho Racket Base, as well as the functions and values needed to use parametric randomness. However, you cannot invoke any of the randomness functions outside of a context in which the current random source has been parameterized, or you'll get an error. We felt this was the right approach because we wanted to help users avoid accidentally invoking randomness functions in a non-parametric way. This might not always be what you want, though, so we also provide hashlang Clotho stateful. This is similar to hashlang Clotho, except the current random source will be initialized automatically, just like how hashlang Racket Base works. There are also a few extra forms for manipulating the top-level random source if needed, which are detailed in the documentation. This brings us to the last big question. Why did we go through all of this in the first place? What could we possibly have been up to that required us to develop Clotho? Well, we work on a project called Xsmith, which is the spiritual successor to CSmith, if you've heard of that. Xsmith is a library for building effective fuzz testers for any language you like by taking a language specification and producing random programs written in that language. But the problem space for generating random programs is absolutely gigantic, and this corresponds to an enormous tree of randomly made decisions. If one of the randomly generated programs reveals an attribute that is interesting, for example, perhaps it causes a bug despite your specification being correct, then you probably want to investigate nearby branches of the decision tree to see if there are adjacent interesting programs. While investigating what other people have done to accomplish this, we found the recently published paper, Semantic Fuzzing with Zest. While implementing the solution within Xsmith, we decided to instead generalize the library and make it available for use in other domains. Hence, Clotho was born. Our work on this is pretty recent, so we do not yet have any concrete results to share, but we are excited to see what the future holds for Xsmith and Clotho. With that, we've pretty much covered all of Clotho. Let's review what we've learned. We defined parametric randomness, a special system of random generation where each random generation event can be correlated to a specific tunable parameter. These parameters can then be fed back in to essentially rerun the sequence of random generations, but with changes that will produce changes in predictable locations in the output. We found that Racket's built-in randomness functionality is simply insufficient for doing this by hand. I should point out that this is reasonable, of course. Parametric randomness is a fairly niche use case, as far as we can tell. But since we wanted parametric randomness, we implemented it in the form of Clotho, a Racket library that solves all of your problems in life, so long as those problems are solved by easy parametric randomness. So where can you get Clotho? Well, we recommend just using the Racket package manager. A quick Racco package install Clotho should do the trick. But if you're really keen on going through the source code, or if you want to file a ticket on our issue tracker, you can access Clotho's Git repository at this URL. Well, that's it. I hope you enjoyed this talk about Clotho, a Racket library for parametric randomness, a paper brought to you by Pierce Dara, that's me, William Hatch, and Eric Eide. Please feel free to contact us with any questions or comments. Thank you.
Let's see, do we have any questions?
So if there is no question, I have one for you, Pierce.
Sure.
So I understand that the library rely on core features of Racket, but I'm curious to know if you evaluate the effort that will be required to port the library to a different scheme implementation or to support several scheme implementations.
I'm sorry. Could you repeat the question?
Yeah, sure. So I understand that as you implemented the library, you rely on specific Racket features that will not be easy to port to other scheme implementations.
Oh,
Yeah. So my question is, did you evaluate the efforts that will be required to actually port it to other scheme implementation to support several implementation of scheme?
we did not evaluate that specifically, but I think it'd be reasonable to say that it wouldn't be too difficult to port. All it really relies on is having an existing way of generating some kind of random value that you can seed. So in the talk I mentioned that kind of an issue with Racket's existing thing is that sure, you can supply a seed value to start the random generation down a determined path, but you don't get any fine-grained control over each call to the random generation function. You only get to seed the initial value and then just see where it goes. But you can use the seed to generate a single value, and that's kind of what Clotho relies on. So as long as whatever scheme implementation or whatever, any language really you're using, as long as you have a way of generating a single value that you can exert some control over through the form of a seed, then you could re-implement Clotho.
Okay, I see. Thank you, and thank you for the presentation. It was really interesting. Thanks.
Yeah, for sure. Thank you.
I've got a question.
Sure. Hi, Will.
Hi. Very nice talk. So could you use this for things like program synthesis? I mean, it seems like you're being able to select which randomly chosen programs you care about, right?
Mm-hmm.
And also, how would this compare to using like Markov chain Monte Carlo techniques and the sort of fuzzing things that you get with stochastic super optimization and Stoke, if you've seen that. It feels like that there may be some applications kind of like that, but I don't know how the performance would work, or if it'd be comparable performance wise.
So let's see, a couple questions there, but I guess the first one was whether we could use this for like program synthesis. Yes and no. It is a little complex, I guess. So yes, in the sense, we do use it for program synthesis in XSmith. We are working on integrating it into XSmith. It's a little complex, I guess. So it kind of comes down to the issue that I addressed with the randomness abstraction section, where I talked about how okay, so if you don't use randomness abstraction, if you just use the single top-level byte string for all of your random generation events, then what can happen is if you go back and manipulate something early in the sequence, then it can have kind of unexpected consequences later, depending on what kind of thing you're changing. So if you end up replacing, the generation of an integer value with like an if statement, now you've got a problem because all of your sequence of random values will now shift semantically. In the paper, we kind of muse a little bit about like maybe we could have an alternate representation that could encode some of this information, and then you could manipulate things only in certain ways so that you don't have these kinds of problems. But we haven't done that yet. Okay. So I guess that's the first answer to your first question. As far as other more complex methods of random generation and things, I can't say that I am well versed enough to be able to really answer that adequately, I think.
Okay, thank you.
Yeah. I see William put a question in the chat. So he asked if we thought about integrating this into redx's generator. I guess the answer is no, if only because just haven't gotten to it, I guess. I don't use redx personally. Nothing personal, but I just don't have the occasion to. But maybe it could be useful there. I guess that's kind of the same sort of idea with program synthesis, maybe. So definitely something you could do, but there would be some implications if you, like I said, change things early in the byte string sequence.
Okay, so I think that's it for the question. Thank you, Pierce. Thank you very much for the presentation.
Yeah, thanks for having me.